Hello, in this video we're going to talk about Thevenin's equivalent. Let's start with this first example. We have here a circuit with two current sources and three resistors, and then we have a load connected to this circuit. And we want to find the Thevenin's equivalent. And we're also interested in finding the value of the current flowing through the load when the load is zero. And we're going to be using the equivalent circuit to do this. This current is also known as ISC, which means I short circuit. Here we have two current sources, four resistors, and then we have the load connected between these 2 points. We want to find the Thevenin's equivalent. That basically means we need to find two things. One is R Thevenin, that's the value of the resistance, and the other thing we need to find is V Thevenin, that's the value of the voltage. So let's start with R Thevenin. In order to find R Thevenin, we have to get rid of the sources in the circuit. So we replace current sources with open circuits and voltage sources with short circuits. In this case, we only have two current sources. So what we're going to do is we're going to redraw the circuit, but instead of the current sources, we're going to put a short circuit there. No, we're going to put an open circuit there. So we have the resistors, 10, 5, and now we have an open circuit instead of the 1 amp source. And then we have here the 2 amp source, and what we have there is just an open circuit. Then we have the 30 ohm resistor, and here we have the load. Now the next step is we have to find the equivalent resistance connected between the 2 points of the load. The first thing to notice here is the 10 ohm resistor is basically disconnected from the circuit, so we can just remove it. And we end up with a circuit like this with 5 ohms here, 20. Here we have the open circuit, then here we have 30, and here we have the load. Now we have a similar situation here because 20 and 5, they're in series. We can combine them, but again we have an open circuit here, so this whole thing is disconnected from the circuit. We can just remove it, and we end up with one resistor, 30 ohms, and then the load RL. Then here we stop because we have just one resistor connected to the 2 points of the load, the 2 terminals of the load. So that's it, we have found our Thevenin. And in this case our Thevenin is 30 ohms. Now the second step is to find V Thevenin. And to do that we have to work with the original circuit, with all the sources and all the resistors in the original circuit. What we do is we take the load to be infinite, in other words it behaves like an open circuit, or we can just disconnect the load from the original circuit. That's what it means. So we can redraw. Let's redraw the circuit with an open circuit in the load. So what we have is something like this. This is the original circuit, then we have the load. But we have to disconnect the load. That basically means we can just remove it from the circuit. Once we remove the load, we're interested in finding the V open circuit. And that V open circuit, in this case, is between these 2 terminals, corresponds to the voltage across the 30 ohm resistor. So V open circuit is the V Thevenin we're looking for, and in this case, that is simply the voltage across the 30 ohm resistor. So we basically need to find the current flowing through this resistor so we can apply Ohm's law to get the voltage we're looking for. Since we have an open circuit, all of the current flowing through the 30 ohm is the same current flowing through the 20 ohm. And here we have just two current sources. This one is providing 1 amp and this other one is providing 2 amps. So we can easily find this current I applying Kirchhoff current law. Here we have that the current I has to be equal to 1 amp flowing here plus 2 amps flowing there, and we get 3 amps. Now that we have the current, we can easily find the voltage across the 30 ohm resistor by taking 30 ohms, multiplying that by 3 amps, and we get 90 volts. And that's the V30 volts. That is exactly equal to Thevenin. So we're done. Now we can draw the equivalent circuit. The equivalent circuit has one voltage source and one resistance. The voltage source has 90 volts, that's Thevenin, and the resistance is Thevenin, in this case is 30 ohms. So we have 30 ohms there. In between these 2 points we have the load. So this circuit here has the same VI characteristic than the original circuit. Now for part B, we have that the load is 0, so we basically have a short circuit. And we want to find the current flowing through the load. That's the question. So instead of working with the original circuit, we're going to use the equivalent circuit, because we can easily find the current just by applying Ohm's law. So we have the voltage source with 90 volts, then we have the load is 0, so we basically have a short circuit, and then we have our Thevenin here is 30 ohms, and we want to find this current IL. So what we do is basically Ohm's law. We have just one resistor, one source, so we get 3 amps, and that's I short circuit, or the current through the load when the load is 0. Now in this second example, we have a circuit with one voltage source and one current source, and we want to find the Thevenin's equivalent as well. So we have here a current source. So when we have here the current source, 3 resistors, then we have the voltage source between these 2 points, 4K and 8K, then we have the load. We want to find Thevenin's equivalent. That basically means we have to find R Thevenin and V Thevenin. So let's start with R Thevenin. We replace the sources. In this case we have 2. So we replace the 2 milliamps source with an open circuit. Then we have the 3K. So here we have the source has been replaced with an open circuit. Then we have 6K. Now we have the 2K. Now the 12 volt source, we replace that with a short circuit that is basically just a wire. Then we have the 4K and 8K. So 4K here and 8K there. And here we have the load. Now we have to simplify the circuit to get just one resistor connected between the 2 points of the load. We have the 3K disconnected, so we can just remove this because we have an open circuit there. Now we have 2 and 6 in series, so we can just combine them in one. That is 8K. Now we have the short circuit there. Then we have the 4K here and the 8K over there. And don't forget about the load. Now we have a situation here where 8K is in parallel with a short circuit. Every time we have this situation, when we have a resistor that is in parallel with 0, 0 is the short circuit, we have 0 as the equivalent. So we can replace the 8K and the short circuit with just the short circuit. So we end up with something like this. With the short circuit instead of the 8K in the short, and here we have the 4K, and here we have the 8K, and then the load. And what we have now here is, well, we have the 8K in short with the circuit. Now we have just a short circuit. What we have now is the 4K. The 4K resistor, it's in parallel with the 8K. That's basically our R-Thevenin we're looking for. So R-Thevenin in this case is just 4K in parallel with 8K, and that number is 2.67 kilo. That's R-Thevenin. The second step now is to V-Thevenin. Okay. So we have to work with we have to disconnect the load, find the open circuit, and that the open circuit is going to be the voltage V-Thevenin we're looking for. So we have to work with the original circuit. We redraw the original circuit, but now we remove the load, so we have an open circuit there, and we're interested in finding this V-open circuit. That's our V-Thevenin. So V-open circuit is equal to V-Thevenin. In this case, we have the V-open circuit we're looking for is the same voltage across the 8K ohm resistor. So we basically need to find this current flowing here so that we can apply Ohm's law to get the open circuit. We have zero current flowing there because we have an open circuit in the load. So the same current flowing through the 8K is the same current flowing through the 4K. Now in this circuit we have 3 loops, but we just need to work with the last one in order to find the current. So there's no need to work with the rest of the circuit. Let me just apply Kirchhoff voltage law in this loop, and you'll see that we can easily find the current that we're looking for. So 12 volts is the gain, and we have 2 drops. The drop across the 4K and the drop across the 8K. Now the drop across 4K is just the current I times the resistance 4K, plus the drop across 8K is the same current I times 8K. So we have just one equation, one unknown, and from this equation we can find the current. So from here we have I is 1 milliamp. So there's no need to work with the rest of the circuit in this case. Just analyzing this this loop, we can easily find the current, and now we can find the volts across the 8K. And that's the current times the resistance. 8K times 1 milliamp, that's 8 volts. That's the volts across the 8K resistor, and that is V-Thevenin we're looking for. So now we can draw the equivalent circuit. It has one source, one voltage source, that in this case V-Thevenin is 8 volts. So we put there 8 volts, and here the resistance R-Thevenin 2.67 kilo ohms, and the load. So now we can just use the equivalent circuit to find any value of the current given any value of the load instead of working with the original circuit.